Next two examples are a little bit trickier to set up, but don't worry, we won't go through the integrating by hand, so we'll just leave it as an integral expression. So our first one, write an integral expression of the area of the inner loop. That's everything in here. And in order to do that, what we need to think about is what is the r when theta starts? So when theta is 0, the r will be 1 plus 2 times the sine of 0, or just 1. So we start here. That is the beginning part. So if we want to do just the inner loop, and this is similar to what we saw last class with the arc length, we can't start when theta equals 0, because if we start there, we'd be including all of this area in the outer loop. So if we want to just include the inner loop, we need to start when that r comes down to 0. And that'll be the start of our inner loop. We can see it somewhere in the third quadrant. When theta equals pi, and we're about to move into the third quadrant, the r is 1. And then the r is getting smaller and smaller and smaller, because sine starts getting negative, until finally the 2 sine of theta is more negative than the 1 is positive, and our r becomes negative. So what we want to look for is where is that magic spot in the middle where that r becomes 0. And that's what we're going to find. When does the r equal 0? 0 equals 1 plus 2 sine theta, and this one happens to be one you can solve by hand. Negative 1 and then divide by 2 equals sine of theta. And that is the sine of one of our special angles. The sine of pi over 6 is 1/2, and because we're talking in the third quadrant, that means that theta is equal to 0 when the sine is equal to 7 pi over 6. And again in the fourth quadrant, when theta is equal to 11 pi over 6. So those are our starting and ending points, which means the area that we're looking for is 1/2 times the definite integral from 7 pi over 6 to 11 pi over 6, forgot my pi, of r squared d theta. And that one's not too bad. The next one is a tiny bit trickier. We want to write an integral expression of the area between the two loops. So we're talking about everything out here in all of this section right here. Now, based on what we saw earlier in the year with areas and volumes, we kind of have a hunch that that's going to mean finding the area of the whole thing and then subtracting the part from the inner loop. There's a catch to that, though. If we start by saying that we're going to find the area of the whole thing and then subtract the inner loop, that might look like this. The area of the outer, just the outer part, would be the area of the entire trip around. Sorry, I forgot my 1/2 times r squared d theta minus the integral we just wrote, which is the area of that inner loop. One plus 2 sine of theta squared d theta. But there's a problem with this. And to see the problem, let's look to our Desmos graph again. And here's the graph of 1 plus 2 sine of theta. And look what happens when I sweep the area out, starting from 0. And by the way, it's okay that we start from 0 and not from like negative pi over 6 like we did for the arc length. But look what's happening as I sweep this out. So just as I suspected before, we are sweeping out the area including the inner area, which we don't want. So we're going to have to subtract that. But as I continue going around, notice what happens as I get past 7 pi over 6. I'm sweeping out that inner area again. So if I were to keep adding up all these infinitely small little sectors, I'd be I have already added the inner loop once when I went around and included the entire shape, and now I'm doing just the inner loop again. So it's not enough to subtract the inner loop once. Since I counted it twice in my area, if I really don't want it to be a part of my final answer, I would need to subtract that inner loop twice. And what I'm left with would be the area of just the outer loop. So 1/2 the definite integral from 0 to 2 pi of 1 plus 2 sine of theta squared in respect to theta, minus the 2 times 1/2 cancel each other out. So the definite integral from 7 pi over 6 to 11 pi over 6 of r squared theta in respect to theta.